We're continuing with chapter 11. In this video, we're going to go through section 11.3, which is on the integral test and estimates of sums. Now, in the previous video, I talked about how, starting with this section and for the next 5 sections, we're going to be learning how to test series to see if they converge or diverge. And I talked about why, for non-math majors, being able to do these tests on series is important. Okay, so it says, in general, it is difficult to find the exact sum of a series. We were able to accomplish this for geometric series, and this was the telescoping series, because in each of those cases, we could find a simple formula for the nth partial sum, S sub n. We found S sub n for geometric series. Also, in one of the algebra videos that's included in the playlist, we found S sub n for arithmetic series. And then we saw for special cases for like telescoping series, we could get the S sub n. But then there's also cases where you could like write out the first 5 or 6 terms of the S sub n formula. And then you could, from those first 5 or 6 terms, develop a expression of n that works for those first 5 terms, and then use mathematical induction to prove that formula is true for all n. Okay. And so once you have an S sub n for a series, then when it comes to analyzing the series, you're home free. Because what you start with is, in general, you're going to, if you're working in practice or you're trying to solve a problem in engineering, physics, biology, chemistry, wherever, you would have some sequence. So you have a sequence, the sequence formula, you have a sequence. But then you're thinking about the corresponding series for that sequence. And so that's where you put it into a summation. So you start with this, you have this. And so if it's not geometric or arithmetic or telescoping, like you can solve it with some trick, then you could always write out the first 5 or 6 terms of the S sub n, come up with a function of n for that S sub n sequence, and then use induction to prove it for all n. And again, so once you have the S sub n that's valid for all n, you're home free when it comes to analyzing the series, because you could just take the limit as n goes to infinity for that S sub n. If it's divergent, then you know it's divergent. You know how it's divergent. If it's convergent, then whatever the limit is what it converges to. Okay, but it says, usually it isn't easy to discover such a formula. Therefore, in the next few sections, we develop several tests that enable us to determine whether a series is convergent or divergent without explicitly finding its sum. Okay, and so this is what I talked about in more detail in the previous video. You might be wondering, well, okay, so usually it's not easy to get an S sub n for, when you have a series like this, but we're going to go through all of this work in the upcoming 4 or 5 sections to be able to test to see if a series like this is convergent or divergent, even if we can't find the sum. So, but what's the point of that for a non-mathematician? Why do we care just to know if a series is convergent or divergent? Well, because what we're going to talk about for the second part of this section is we'll be able to get estimates of sums. And for a non-engineer, estimates are fine. As you can get estimates usually however accurate you want. I mean, in general, like you can get it very accurate, like within, point something percent, 0.0 something percent, or even more than that with computers. Okay. And so, but before you get an estimate for the sum, you want to state for a fact that this is convergent. Right? You want to say, okay, this is definitely convergent. Now, what's an estimate for the sum? Or you'd want to, if you find out that it's divergent, then now you know it's divergent. So you can't use it as like a sum. So these tests for convergence or divergence of series is really valuable for non-math majors when you consider that we can still, even if we can't find the sum, the exact infinite sum, we can still get an estimate for the sum. Okay, we're going to talk about these estimates of sums at the second part of this section. Okay, but what we're going to do first is we're going to go over the integral test. And this is with the integral test, this is where improper integrals come into play, which we learned about in section 7.8. So it says, we begin by investigating the series whose terms are the reciprocals of the squares of the positive integers. Okay, the reciprocals of the squares of the positive integers start at 1 and then go to infinity. The sum of the reciprocals of the squares of the positive integers. There's no simple formula for the sum of the first n terms, but the computer-generated table of approximate values given in the margin suggests that the partial sums are approaching a number near 1.64. So it says there's no simple sum for the S sub n, right? The S sub n would be, the first term for the S sub n would be 1 over 1, would just be 1. The second term would be 1/4 plus 1. The third term of the S sub n would be 1/9 plus 1/4 plus 1. And it's saying there's no simple formula for the S sub n. Because if you have the S sub n, then there's no need to do a convergence test, right? If you got the S sub n, then just take the limit of the S sub n as n goes to infinity, and that'll tell you everything you need to know. So these convergence tests are, when you can't get the S sub n for a series. So you can't get it. There's no way to get a simple formula for the S sub n here. But then what it does is you can still calculate any term of the partial sum because you have this, right? You might not be able to get a formula that's just a strict function of n, but you can calculate any term of the partial sum because you have this. Just put in whatever term you want. That's what they're doing here. This is when the sum when n is equal to 5, 10, 50. You've got the a sub n. And so it says, you can, for any series, you can start out by doing this with your computer and seeing does it look to converge to something. Now, this isn't going to give you an official answer for if it's convergent or divergent, but it can give you a hint. And this looks like it's converging to something. Approaching a number near 1.64 as n approaches infinity. We can confirm this impression that it's convergent with a geometric argument. Figure 1 shows the curve y is equal to 1 over x squared and rectangles that lie below the curve. Okay, so y is equal to 1 over x squared. We looked at this formula from the perspective of an improper integral in section 7.8. So here's y is equal to 1 over x squared. And then you've got these rectangles that lie below y is equal to 1 over x squared. The base of each rectangle is of length 1, right? It's between the integers. And the height is equal to the value of the function at the right endpoint of each of these intervals. You see? So this is the height of this rectangle is this function evaluated at 2. The height of this rectangle is 1 over x squared evaluated at 3. Okay, and so it says the sum of the areas of the rectangles is 1 over 1 squared plus 1 over 2 squared plus 1 over 3 squared, which is the sum from n is equal to 1 to infinity of 1 over n squared. So if we come back, what are they saying? Yeah, so each of these has base length 1. So the area is just the height of the rectangle, which is 1 over the right endpoint squared. So this area is 1 over 1 squared. This area is 1 over 2 squared. This area is 1 over 3 squared, 1 over 4 squared. Okay, and so you agree that the area of the rectangles is as shown here. That's the series we're looking at. We're analyzing. If we exclude the first rectangle, the total area of the remaining rectangles is smaller than the area under the curve for the y is equal to 1 over x squared for x is greater than or equal to 1, which is the value of this improper integral. So if we come back, what they're saying is we're going to be looking at the improper integral of going from 1 to infinity of 1 over x squared, because we don't want to have start at 0, since we'll have to use the improper integral part 2 in that case. We want to start at 1 because we can't divide by 0, so we're going to start at 1. We're thinking about the improper integral from 1 to infinity of 1 over x squared. So what it's saying is, so in that case, let's exclude this area, and you can see that for sure the area under the curve, the improper integral from 1 to infinity of 1 over x squared, is definitely going to be greater than or equal to the area of the rectangles starting at, it would be at n is equal to 2. Okay, so it says, in section 7.8, we discovered that this improper integral is convergent and has value 1. So We found this here in section 7.8. Okay, so the picture shows that all the partial sums are less than, and they take this improper integral here and then add this 1 over 1 squared to it. They're all less than 2. Yeah, there's no matter what you plug in to, if we come here, no matter what you plug in here, you'll never get something that's greater than or equal to 2, no matter what. And they just added the 1 back, the 1 over 1 squared, so we can include the whole summation, right? And so what they're just saying is from 1 to infinity, this improper integral is 1. That's obviously less than the sum of all of these rectangles. But then if you just add this back, you're not changing anything with respect to the inequality. Like, it's not like we said, okay, the any partial sum that you evaluate will always be less than, and so the integral from 1 to infinity of 1 over x squared dx is 1, and then we added 1/2 to that. Because then you could say, oh, well, but this area is 1. So maybe you could, this extra area here that you didn't include in the inequality could make up for the fact that this is always less than with the area under the curve. But all we did was just add 1 to the inequality. So the additional, so no matter what you do going from 1 to infinity, going from here to infinity, obviously you can never get an area of the, and as far as the sequence 1 over n squared, you could never get an area that's greater than or equal to the area under this curve. Now, maybe if we could do something with this rectangle, if we can include this rectangle, we could somehow catch, like the idea of having the sum of the sequence be greater than the area under this curve. But all we did, we added 1. The fact that this area under this curve from 1 to infinity of 1 over x squared dx is 1. And then we added 1 to that and said that, okay, this total sum of the sequence could never be greater than or equal to the area under this curve from 1 to infinity plus 1, well, then obviously we haven't changed anything. Okay, so no matter what you plug into the partial sum, you'll never, using this improper integral here, we can see that no matter what value you plug in to the partial sum of 1 over n squared summation, you'll never get something that's greater than or equal to 2. Thus, the partial sums are bounded. So they're definitely bounded above, and so, but bounded means you're bounded above and below, and it's obvious from the formula that they're bounded below, like at 0, let's say, by 0. They're bounded above by 2 and below by 0. I don't know if that's the actual literal, the capital M would be the actual series sum, what they're actually bounded above by, but just to show that they're bounded, they're definitely bounded above by just a random number would be 2 and below by 0. So they're bounded. The partial sums are bounded. We also know that the partial sums are increasing because all the terms are positive. That's how we know that it's bounded below. Therefore, the partial sums converge by the monotonic sequence theorem, and so the series is convergent. Okay, so you see what they're saying here, that it's the fact that we don't have a partial sum formula, like an explicit function of n. But we do have the partial sum as a summation. Okay, and so since we were able to show for sure that, like, okay, this is a sequence, right? You can write S sub n as a sequence. We were able to show that this S sub n sequence is bounded above and below, so it's bounded. And we also showed that it's increasing, so it's monotonic. And therefore, we know from the monotonic sequence theorem, we're talking about the sequence S sub n, that the sequence S sub n is convergent, which means that the series is convergent. Again, we haven't evaluated what the S sub n is as like an explicit function of n. We've just shown that the sequence S sub n is convergent. The sequence represents the series. The sequence S sub n represents the series. The sum of the series, the limit of the partial sums, is also less than 2. Yeah, it's definitely less than 2, but we don't know the actual limiting upper value would be that what the series is, the answer to the series. We don't know that. The exact sum of this series was found by the Swiss mathematician Leonhard Euler to be pi squared over 6. That's what it's truly bounded above by. That's the series. But the proof of this fact is quite difficult. Okay, now let's look at the series 1 over the square root of n. The table of values of S of n suggests that the partial sums aren't approaching a finite number, so we suspect that the given series may be divergent. Yeah, so they do the same process. They evaluate the S of n, which, we can do that. We don't have a formula for it, at different numbers, but it doesn't look like it's converging this time. Again, we use a picture for confirmation. Figure 2 shows the curve y is equal to 1 over the square root of x, the continuous curve. But this time we use rectangles whose tops lie above the curve. Okay, so they're evaluated at the left endpoint this time. And we're starting at 1. The base of each rectangle is length 1, and the height is based on the left endpoint. So when you think about the areas of these rectangles, it's 1 over square root of 1 plus 1 over square root of 2 plus 1 over square root of 3, which is equal to the sequence, which this total area is greater than the area under the curve. Y is equal to 1 over square root of x, for x is greater than or equal to 1, which is equal to the integral from 1 to infinity of 1 over square root of x dx. But we know from section 7.8 that this improper integral is divergent. In other words, the area under the curve is infinite, so the sum of the series must be infinite. That is, the series is divergent. Okay, so if we come back, we know that from the improper integral section, if you take the integral from 1 to infinity of 1 over square root of x dx, this is divergent. But clearly, this area, the area represented by this integral, is less than or equal to this sequence here. The sum from n is equal to 1 to infinity of 1 over square root of n, because this sequence is represented by the areas of these rectangles. And so, since the sequence the area is definitely it's greater than or at best equal to a area that's divergent, then the series is going to be divergent. Okay? Now, this is a little confusing because of how this is set up, but so, okay, what we were trying to, let's, for the case of the convergence case, we were trying to use this improper integral here as a comparison to the series, a series. Okay, this is the series, right? But since we wanted to set this up in a way because we knew this was convergent, so we looked at it from the standpoint of left endpoint, the left endpoint convention. So the areas of the rectangles would be less than the area under the curve, and we did it that way to where we were just talking about going from n is equal to 2 to infinity of 1 over n squared. That's what this integral represented. Since we were using the left endpoints, we compared this integral to this sum going from starting at 2, which we found that this was, no matter what, less than or equal to this sum starting at 2, starting here. But then what we did was, just to do the full comparison, because we're looking at this full sequence, we just added 1 to both sides. We said that, okay, since we're trying to compare this full sequence, but we want to use the left endpoint convention because we feel like this is going to be a convergence, then we set it up with the left endpoint convention. We said that, okay, well, this series sum starting at n is equal to 2 is going to be, no matter what, less than this. But then to accommodate this entire series, which has the 1 over 1 squared in it, we just said, okay, well, then it's going to be less than, this entire series is less than this plus 1. Kind of like added 1 to both sides. Here, we were looking at it from the divergence perspective, so we wanted to use this would be the left endpoints. Yeah, we used the right endpoints over here. I might have said that wrong just now. We used the right endpoints here to make sure that the rectangles were less than the curve, the improper integral curve. Here, we used the left endpoints, and we didn't need to, in this case, we didn't need to like start at the second term of the series. We could just, the areas of the rectangles in comparison to going from 1 to infinity of this improper integral, or you just set them equal to each other. There's no need to like add something to both sides after. Okay. All right. The same sort of geometric reasoning that we used for these two series can be used to prove the following test. So what they're saying is that we use these improper integrals to validate or to state whether a series was convergent or divergent. We just showed that, the idea of doing that. So with that, there must be an official kind of procedure we can use, an official test that we can use improper integrals to check if a series is convergent or divergent. Yeah, and so this is the integral test. Suppose we have a function is continuous, positive, decreasing function on 1 to infinity, and let a sub n, the sequence, equal to f of n. All right, so we've got a function. This has nothing to do with sequence. Any function of x. It's continuous, it's positive, it's decreasing on the interval from 1 to infinity. So what does that mean? This is 1, it's continuous, right? We know what continuous means. It's positive. It's always, for 1 to infinity, it's always above the x-axis, and it's decreasing, right? So decreasing, it's always, the next term is always less than the previous term. And then, so, well, since it's continuous, if that's the case, if these three parameters are the case, then you have no issue just making a sequence formula that you just take the f of x and replace the x with the integers in, going from 1 to infinity. Okay, then the series, where if you put that a sub n into a series starting at 1, that series is convergent if and only if the improper integral going from 1 to infinity of f of x is convergent. So this isn't the greatest test in the whole world, because we're restricted to continuous positive decreasing functions, but still, it's a test. Right, and so you can use this integral test if you have this case. If the improper integral is convergent, then the series is convergent. If the improper integral is divergent, then the series is divergent. Now, if the improper integral is convergent, that doesn't mean that you know what it could, like, it's not like, okay, it's convergent, you actually get this integral is equal to a number, but that number doesn't equal the series. This is just a convergence test. Okay, now, it's important to note about this integral test that, so, okay, when we use the integral test, it is not necessary to start the series or the integral at n is equal to 1. Yeah, and so what they're saying here is that it's stated that everything starts at 1, but you have a lot of flexibility with regard to the start point. So there's two ways to look at this. The series you have doesn't have to start at 1, but the function you have doesn't have to. So this restriction, it says continuous positive decreasing function on 1 to infinity. This doesn't have to be the case, for 1 to infinity. Let's say this was from 20 to infinity. This was the case. Just from 20 to infinity, then you could still use this test. It would be perfectly fine. You would go from 20 to infinity, then you would look at the series going from 20 to infinity. With that, you could prove that the series is convergent from 20 to infinity. And so what would that mean for the actual series itself starting at n is equal to 1? Well, all you would do is you would just go look at it yourself. Going from n is equal to 1 to 20, the only way the entire series, if you prove that going from n is equal to 20 to infinity, the series is convergent, then, but the entire series you're trying to see if it's convergent or not, it starts at 1, then you just analyze going from 1 to 20, what do you have? How would it not be convergent? If it's convergent from 20 to infinity, then what would make it not convergent? Maybe if you had an infinite discontinuity at around n is equal to 3 or something. Then if that's not convergent, then the whole series wouldn't be convergent. But if you've got if it's other than an infinite discontinuity, it's going to be convergent. because you can find the area under anything, right? That's really important. You understand that what this is talking about here. It says everything has to start at 1. It does not. You can do this exact same test starting at any value, starting at 20, starting at 1,000, starting at -50. It doesn't matter. You would do the test. The corresponding series would start at 20 or 5,000 or -50, and then for the portion of the series that you couldn't validate with the integral test, that's easy to figure out if that's going to screw up the convergence or divergence. That's really easy. I hope you see why that's really easy. Even if you had, going from n is equal to 1 to 20, if you had a jump discontinuity, so what? You could. We talked about this. This is completely integrable. Everything is integrable, except for potentially infinite discontinuities, right? You can find this area under the curve. Now, when it comes to this area, you have to treat this like a improper integral type 2, but that has nothing to do with the fact that this is 100% going to be convergent. Something that looks like this. Everything is convergent except for potentially if you had an infinite discontinuity, right? So if it was convergent going from 20 to infinity, and then you're checking from 1 to 20, if at like 3 you had an infinite discontinuity, well, then you're going to need to use the type 2 improper integral method to check does this converge or not. If this converges, then the whole series is convergent, because you checked that going off to infinity it's convergent. Now you need to check this and this kind of infinity, but outside of vertical asymptote, or like going off to infinity, like down the x-axis, then there's no issue with finding areas under curves, no matter what the situation, unless like the function doesn't exist. Yeah, I guess if the function didn't exist, but that's different. I mean, then that wouldn't be a part of the problem anyway. Okay, so here's an example. Here's this series. We want to use the integral test to see if it's convergent or divergent. And we can only use the integral test if this is continuous, positive, and decreasing, starting at n is equal to 1, or at least for some value starts at greater than 1. That's the case. Well, this is continuous, positive, and decreasing on 1 to infinity. So we can go ahead and do the integral test with the improper integral starting at 1 going to infinity. This integral equals pi over 4. So that proves that this sequence is convergent. And you might be saying, well, okay, but how does this work? How do we know it's convergent? It comes from this. The continuous, positive, decreasing. Because of that constraint, then when you compare the improper integral to the series sum, it's always something like this. Because of it's continuous, positive, and decreasing, you're doing a comparison just like this with the integral test. If it wasn't continuous, positive, and decreasing, then it wouldn't necessarily set up this way. Okay, so that's where the integral test comes from. Again, it's important. It needs to be the continuous, positive, and decreasing, the lower limit of integration to infinity of the improper integral. The function you're using to do the integral test with, the function of x, needs to be continuous, positive, and decreasing from the lower limit of the integration to infinity. And remember, the function is the sequence. Just you took out the n and put an x, right? We're not choosing any function here. It's not like we can do this for any function. This function we're doing the improper integral on is the sequence formula, but you took the n out and put an x. And so that's why it's like the heights of the rectangles that correspond to the series are like lined up with the x curve. So the function is continuous, positive, and increasing, but then by the definition of the integral test, the corresponding series is, there's no continuous, but it's positive and decreasing, right? If the function is continuous, positive, and decreasing on 1 to infinity, then 100%, because we're just taking, we're taking f of x and putting in the integer for the series, the sequence corresponding to the series, then there's no such thing as a continuous series, but the series is 100% going to be positive and decreasing as well. Okay, so that's how the integral test works. Okay, and so that's why this series here, if you take the n out and replace this sequence formula with an x, that function of x is continuous, positive, and decreasing, going from 1 to infinity as well. Then you do the improper integral, and since that integral converges, that means this series converges. If this diverges, that means this series would diverge. Okay, the next example says, for what values of p is the series, this series, convergent? Okay, so how do we approach this? Well, when it comes to the integral test, we replace for the a sub n, we replace the n with an x, and we look and see, okay, is this f of x continuous, positive, and decreasing, either over going from the entire range of the series, so like we would say as x is starting at 1 to infinity, or at least at some starting point, is that the case that's continuous, positive, and decreasing? Well, 1 over x to the p, where p is just like any real number, for certain values of p, that is the case. That f of x is continuous, positive, and decreasing, going from 1 to infinity. Okay, but it says if p is less than 0, then, so what do you do here? P is less than 0. So if p is less than 0, then you don't, it's not, the series is not decreasing, right? The series is increasing. So you can't use the integral test. So what do you do? Well, remember, there's always the option. We did learn in the previous section, we learned how that we can test. There's ways to test if a series is convergent or divergent that we learned before this. And remember, that test was that if you could find the limit of the sequence, right? So before this section, if we had a series like this, we could test for convergence by taking the limit of a sub n. If the limit of a sub n doesn't converge to 0, then we know that the series is divergent. If it converges to 0, then we don't really know anything. They call this a test for divergence. It was more of a test for divergence. If this limit is equal to 0, then we don't know if it's convergent or divergent. It's only about testing for divergence. If this limit is anything but 0, then we know the series is divergent. So if p is less than 0, then the a sub n doesn't, the limit of it isn't 0, so we know that the series is divergent. If p is equal to 0, then the limit of the sequence is 1. That's not 0, so diverges. The series diverges. This was the test for divergence that we learned in the limits of series section, the previous section. Okay, but if p is, the last option is p is greater than 0, then f of x is, for x is 1 to infinity, this function is continuous, positive, and decreasing. Okay, so now we can use the integral test. Agreed? That's the first thing. You have to check, is this continuous, positive, or decreasing, going from the range of the series you're looking at, the entire range, or at least a portion of the range. Well, for the entire range here, this is continuous, positive, and decreasing when p is greater than 0. So, okay, now in chapter 7 on improper integrals, we analyzed this function from the improper integral standpoint, and we found that it converges if p is greater than 1 and diverges if p is less than or equal to 1. Well, okay, so it converges. For the case we're looking at, p is greater than 1, this converges. So by the integral test, which we just defined, this series is convergent when p is greater than 0. Okay, now again, the integral test, this is the big constraint when it comes to the integral test. Don't forget that. Okay, so they call this the p series, sum from n is equal to 1 to infinity of 1 over n to the p, is convergent if p is greater than 1 and divergent if p is less than or equal to 1. Okay, cool. So they do an example here, and they note that the integral test, we don't say the value of the improper integral is equal to the series, not at all. I already mentioned that. Okay, determine whether this series converges or diverges. So, okay, replace the n with an x here. Natural log of x over x. That function is positive and continuous for x is greater than 1 because the logarithm function is continuous. But is it decreasing? So what do? They compute the derivative. And so here's the derivative. And if you solve for when this is positive or negative, it's only when x is greater than e do you have a decreasing function. So they do the integral test, and it looks like they just start at 1 anyway. I'm not sure why they would do that. To me, you would integrate from e to infinity, and if that converges, of the function of x, if that converges, then you just go back and analyze from 1 to e. Is there anything weird going on? But actually, I think if we come here, it says, so the integral test, it is not necessary to start the series at n is equal to 1. So you could you could start at 4, for example, and you do the improper integral starting at 4. The sequence or the series starts at 4. And it says it's not necessary that f be always decreasing. What is important is that f be ultimately decreasing. That it is decreasing for x larger than some number n. Then the sum from n is equal to that number n to infinity of a sub n is convergent. And so that means starting at 1, it's also convergent by note 4 of section 11.2, right? That's what we talked about. So yeah, I mean, if you can think about it however you want. I mean, to me, you just start it at, the idea would be if this is convergent from e to infinity, okay, what's that saying? That's saying that, so e is equal to like 2.7 something, okay? So if we come here, what that's saying is that if you start this at, so n is equal to 3, that's above 2.7, that if you integrated this from e to infinity and you got a value, that means that this is convergent from n is equal to 3 to infinity. Okay, so is it convergent from n is equal to 1 to infinity? Well, of course it is, because you just have, to that convergent value, that sum from 3 to infinity, you're adding the first term and the second term. You would just go look at the series before the value that you apply the integral test to and see if there's anything weird going on. And I guess with the series, there wouldn't be. It would just be the terms before that. Yeah, exactly. I mean, unless the series were going off to negative infinity, I mean, that doesn't make any sense. I mean, I hope that makes sense to you. If you prove that a series is convergent from 20 to infinity, then it's convergent from 1 to infinity, because you're just adding the first 20 terms to that convergent value. There's no, right? So what they're saying here is that if you take the n from the a sub n and you replace it with an x, and you get a function it's positive, continuous, and then ultimately decreasing, at least at some point, wherever, could be starting at 300 or wherever, it going to infinity, it's decreasing. So in that sense, you would take the derivative of the function and show that for some number greater than a certain x value, the function, the derivative is always negative. Then you don't even have to take the improper integral starting at that value. You can just take the improper integral starting at the starting sequence value. It doesn't matter. Okay, so I was hoping to talk about estimating sums of series in this video, but this has gone a little longer than I thought it would. So in the next video, we'll talk about estimating the sum of a series.